Okay, good morning. In the next talk, Erwin Erkinger, a software engineer and project manager, will tell us about the process by which the aerospace company develops and designs software safe and reliable. Please give a warm welcome to Erwin.
Thank you very much. I'm really astonished that so many people are interested in that topic. Further on, I have to clarify, this talk is about the software process. At least it's a teaser. It's not a detailed description because the process the aerospace industry is using is quite huge. And no mysteries will be revealed, like why planes don't drop out of the sky. So you've been warned. If you're still interested, I have 3 parts of my talk. An introduction where I just want to try to give you an impression what reliable software could be and what it is for aerospace industry and how it's defined, or how it could be defined. Then the software process in itself, and at least a conclusion where I just think that it's quite good to have an idea of how this process could be used for the Linux community, or open source, or whatever. One thing which is very important for me is that Thomas Cleriel, long time ago, just stated that the greatest fault is to be conscious of none. And that's very important. Faults will be made, errors are inherent. For aerospace industry, it's quite clear, reliable software, there's no way around. But for commercial application, this is also an issue. If we are thinking back in 1990, where $1.9 billion are lost because of misplaced break in a small C program on the AT&T switches. Telephones went out and only the busy line would be held. Of course, the famous Ariane 5 accident in 1960, where a float was forced into an integer in a non-critical component. Or quite new, the Dell web shop just sold PCs for €5 instead of 588 because of a configuration failure. So I think reliable software is also an issue for non-critical applications. And if you have a look at a typical, let's call it web application, it's huge. It's really huge. 10K to 1 million lines of code, heavy reuse of multiple modules, and often the developers are unaware about the underneath architecture. Typical threads, you know more than me, so I just had it on my sheet. So the chance for a serious error is quite high, I would say. But what is reliable software? Reliable software could be defined like it will not produce more errors than specified, because then it's reliable. If you say it will crash every hour and it will do, reliable enough. If you cope with that, fine. But how to specify that, if it's good enough, mean time between failures, error probability, or errors per line of code, which are very funny metrics, by the way, it's up to you how to do that. And also it's up to you how to define an error, if it's critical, minor, or even a feature. And the difference between the fault and the failure, there are huge stacks of documents which describe the differences. As a matter of fact, you define it, what your reliable software will do. And if your definition is true, then it's good enough for your customer if he pays that for and if he takes the software as it is. After that, just have a look at the software development of the aerospace industry. Tom Stoppard, he's maybe known by you for the film Brazil, just stated that if Beethoven has been killed at the age of 22, it would have changed the history of music, but certainly also of avionics. And to understand what the challenges have been made and how long aerospace industry are dealing with that kind of software problems, I want to go a little bit back in the 1969. The Apollo, the whole world was looking at the Apollo landing on the moon, and one small piece was small, in matter of history. This is the small piece. The computer over here has 32 kilobyte of code and 2 KB of RAM. It almost failed due to a procedural error because they just forgot to switch off the rendezvous radar with the main ship, and no one was there on the moon to ping back for the rendezvous radar. By the way, it was funny to see that this is the first stated occurrence of the 404 error I've ever seen, so maybe just a remark. 25 years later, a company called Boeing, maybe known by you, developed the 777, which was completely designed on computers. No line, no sketch was made by hand. And it's a full digital fly-by-wire flight controls. That means every command on the pilot will give is translated to an electronic thing. It's going through a computer and then to the actuators. And it's configurable. That means if you download a new software, it behaves completely different. Especially interesting because passenger planes are different than cargo planes. And if you want to use it for a cargo, then you have to have different avionics and that. And 4.5 million lines of new code have been written, and you can imagine that's quite a lot of code. Until now, no fatal incident has been reported. There is one on tanking on the airfield, but that's it. So you have to imagine it's really a bunch of software which had no failure, which caused a critical incident. And of course, currently the development hasn't stopped. If you have a look at the A380 and 787, where even more complicated scenarios are here, like multi-company, multi-site production, that kind of stuff. So, that's confidential information, I'm sorry. I also don't know that. But there was no bug which was found that caused an incident. And that's, I think, the most important thing. So, till now, it's 40 years of experience, and the aerospace industry developed a guideline called DU 178B. The B stands for the third approach. It was first 178, then 178A, and then B. B seems now to be quite good, and it is a guideline. It's a de facto development standard because it's accepted by the EASA and the FAA, which are the agencies, the government agency, which allow you to produce a plane and then transport passengers with it. So if you want to produce a plane, you have to ask them if they agree with you that you transport people with it and that you just enter the sky. It was developed by the RTCA and the Eurocare, which are not for-profit corporations. Please do not mistake that with non-profit organization. They might make profit, but they're not intended to do. It's more or less a corporation of engineers which give their experience and form guidelines and standards. And the only thing it does, it provides confidence and trust. Because if you have such a big plane and so many developers, they have to go on the same path, and they have to develop in the same type, so that they can trust each other, that they can trust the modules and the components which are developed. But it will not guarantee any safety. So if you develop according to standards and you develop something bad, then it will fail. But it will fail as specified. That's important. The DO 178B is not a standalone guideline. It's embedded in a huge of other standards. I have just took out the most important for them. It's the underlying document is the safety assessment, which just says that if you develop something, it has really to be follow guidelines and coding standards and this kind of stuff. Then you have the top level guideline, which is describing how you have to develop your system. System development is a little bit the high level view on development. It's not dealing with hardware or software. It just says, I have a plane, it shall fly, it shall not crash, and so on and so on. And from that system development, requirements, constraints, and software level will be transported or given to the software development process. Software level is something which I will explain later on. Requirements and constraints, I think that's quite clear. What is required has to be done, and what a constraint is that is a limitation. In the other way around, the software development will give to the system development the software architecture, how the fault containment will be done, and error sources. Error sources are very important because if they can't be handled, or if they're identified in software, then they can handle maybe in hardware. On the hardware side, the similar thing goes on. From the system development, it will go with requirements, constraints, and the hardware level, and it will give back a hardware architecture and fault containment. Maybe it's interesting that there are no lines between software and hardware development. As a matter of fact, there are no connections. The only connection is over the system development. There is a pseudo connection, which is just a design trade-off. If I'm doing things smart enough in hardware, I don't have to do them in software, and vice versa. On guidance, there are some guidance documents also, an FAQ and a ground version. Because if you have something which is related to your plane, but it's located on the ground, it may have different requirements. So, now have a look at this piece in here, the DO178B in itself. That's it, more or less. I don't think you can read that, maybe you can. It's a bunch of documents which are described by this guideline that they have to exist and how they interact with each other. So, and it's a very complex, it's not a very thick document. I think it has 130 pages, but you don't have to, if you don't know where to start from, you will be very confused. Most of the people start at chapter 2.2, which is failure conditions and the software level. The software level is that what I have also mentioned in an earlier thing. It's an interesting thing because it deals what a component can do for your system. Like, if it fails, is it a catastrophic failure? So the plane crashes, will come down, drops to pieces or whatever. Or is it only hazardous? That means it has a large negative impact. Or it has a physical distress and a higher workload on the crew of the plane. And by the way, if there are fatal injuries, that's also a case, then it's hazardous. The interesting thing is that the DO178 and the developers has just recognized that a stressed crew and a heavy workload on a crew also endangers the safety of a plane, because if a pilot doesn't know where to look because of the many blinking lights, he will not see the mountain which is just in front of him. And then it goes to major, is it significant, to minor, where, yeah, you notice it, but yeah, maybe the coffee machine is broken, or it has no effect at all. That's an interesting category because there are components which don't have any effect if they fail. That's very important because if they are identified as that, they either can be replaced or just removed from the system because you don't need it, or they are isolated from the system, just to have that. So every piece of software will get an attribute of its capability on the safety of the plane. So if there, for example, if the primary flight control, it's certainly a level E, because if that fails, the plane drops out of the sky. But maybe the coffee machine is just level D because, yeah, it's inconvenient, but yeah, if it fails, then it fails. But if the coffee machine fails and the captain of the plane is just getting nervous, then it would be higher workload. So even the coffee machine could go to level B. It's a complicated process to really isolate the interconnections between components. And as Ariane 5 has just shown, the component which caused the failure was identified as non-critical and just destroyed the whole rocket. Knowing that, why not certify everything on level A? Because level A needs a lot of attention. The DO in the 78B just identifies them as objectives. Objectives are documents and attributes to documents, like the document has to be very thick or very thin or whatever. No, they're really quite clear definitions how it should look like. And if you go up from no effect to catastrophic, the objectives raise. So if it's just minor, you have 28 objectives, which are quite easy to cover. But if it's a catastrophic one, you have to invest a lot of effort to find that. In addition to that, there is so-called independence, where I will come to later on. And just to look forward, independence means much more effort. This is an example for an objective sheet, where how it is located in the DO 178B. Some objectives in here. High-level requirements are accurate and consistent. That's quite clear that for every level that has to be mandatory or independent. Independent means that someone else has to look for it. But high-level requirements are verifiable. Maybe for level D this is not important. Also the output of this document has to be verified, depending on the category. As you can see here, there is no level E, because E doesn't have any effect and doesn't have any impact, so it's not mentioned. Now let's have a look at the process in itself, because you have seen a lot of documents, how they interact. First of it, if you just have the idea, you want to develop a plane, especially software for a plane, you're writing a so-called PSAC. That's a plan for software aspect of certification. It's a document where you just describe what you're intending to do, and you send this document to the FAA and to the EASA, which will now have a look at you and on your project. It's just the entry of the project. Then you start a so-called software configuration index. This is more or less a list of artifacts you're intending to produce or producing. Documents, source code, test cases, whatever is part of your development will be listed in here. You start that, it's not finished. It will be filled during the project. The next thing what you do, and every good software developer will do that, you're making plans. A plan for how do you intend the development should go on, how you intend the verification should go on. These are really schedules. Really, on May 1st, I will start coding. On May 2nd, it will be finished. And on May 3rd, I will detect that this is not true. But especially in here, it's not one plan, it are 4 plans. For development, for verification, for configuration management, like you want to set up the subversions, and for quality assurance. Quality assurance is a very important thing in here, and I can say that the quality officer is the one who, if he comes to your office, you will have a clean desk or will be questioned. Then, of course, every good development has standards. You have seen coding standards where you just say, okay, if I'm coding in C, I have to have a nice, not every function shall not contain more than 10 lines or not more than 80 characters per line or whatever. Every company and every team has some standards. Also some design standards. We're just describing how you design. That you're doing a paper, that you have some chapters, whatever. And some requirement standards. This means how you write requirements, how you find the requirements. For the D178B, it's just important that they are here. What is in it? I hope this is something smart in it. Having that, you're studying the so-called software lifecycle environment configuration index. It's a fine thing. It's more or less, as index indicates, a list, and the list contains just the tools you are using. It contains the operating system you're just developing to the compiler you're using. The important thing is that everything is listed, because it could be that one part which is in it is critical for the development, like your compiler. If your compiler does nonsense with your source code, then it's also, it has to be looked for it. So it has to be evaluated, and there are very expensive certified compilers if you really have to rely on what's coming out. Anyhow, you have to just list it with the version number you're using so that it can be reproduced. Okay, so that's my environment. Of course, I have my system requirements which just say the plane shall fly. And from that system requirements, I can start developing so-called high-level requirements. It's called software requirement data. It's a high-level view about your software. The software architecture is in it, and algorithms are in it, and it gives you an overview how the software is structured and what components are in it. Having that requirements, you immediately start doing test cases. If you're doing the test cases, if you have a requirement how your software should look like and what function should be in it, you're writing immediately in that case a test for it. After having the high-level requirements, you continue developing the low-level requirements. It's called software design description, which contains a complete and accurate description of your software. Just see here, you haven't written a line of code till now. The low-level description should be good enough to completely describe your source code. It could be seen as a very good documentation. After having that, you can start coding, and you will develop your source code step by step. Of course, this is not one step after another process. You have to start things. So at the time where you development system requirements, the high-level requirements, you can immediately start developing low-level requirements, and you can immediately start source code. But you cannot finalize the low-level requirements before having finalized the high-level requirements. So it's just, that's the reason why it's a little bit stacked in here. And it's quite clear that if you haven't finalized your requirements, you cannot finalize your source code. Otherwise, that would be a failure in the sense of the 178B. Your source code and your verification courses will be tested against each other, and the result, hopefully yes, it runs, will be collected in the so-called software verification results. It's just a list what the outcome of your test cases will be. Sometimes it's an important test case that a function shall fail. That's also a good thing. In the meantime, where you're developing, records will appear like problem reports. You're just collecting your problems, like the source code doesn't behave like specified and this kind of stuff. They have to just be collected. The same as the quality assurance, that the quality officer regularly reports, yes, you have had to look at your table and it was clean. And also configuration management records, like a snapshot was taken at this time with that tag. Having all that and having a good tested software, you can start with the SAS, with the software accomplishment summary, which is the document the FAA and the SAA is interested, which just says, I've done everything, here are the results, that's my process, here are the documents. And with that, you will get a wonderful ribbon, and the FAA will say, yeah, that's good software, and I trust you. So now I want to have a closer look to this requirement process, because I think this is the one which may be reusable for other development on a non-critical area. Everything starts with an idea that you want to build a plane, and system requirements like the plane shall fly, the plane shall carry people, and so on. And of course your system design standards. And every requirement from the system level has just a number, 1, 2, 3, and so on. So if you're starting now a high-level requirement, you just take the system requirement, have a look how you would implement that. You would make functions out of it, you will make algorithms, and so on. So every high-level requirement, every system requirement will get at least one high-level requirement. And during that time, also your software architecture is built up. And that has also some requirements, will be stated in here. It's also allowed to add requirements which are not related to the software architecture or to the system, because some of maintainability or things like that, or if you want to upgrade your software, that is not within the system requirements. But every requirement where it doesn't have a parent above has to be clearly stated, and it has to be explained. What is not allowed is that the system requirement doesn't have a high-level requirement, because that's the first test, and if it doesn't have one, then it's not needed, or you just forgot it. So if you're completely with that area, you can start with the next layer. It's following the same rules. For every high-level requirement, you need at least one low-level requirement. Of course, it's allowed that one low-level requirement satisfies two high-level requirements. No problem with that. So, and again, if you have something which cannot be related to a high-level requirement, it's called derived, by the way, you have to explain it. Sometimes it's because of your software design standard. It says we have to have functions not longer than 20 lines. And of course, here again, no high-level requirement with a low-level requirement has to be satisfied. And having now so many requirements, you can start coding. And of course, the description of the low level is so good that you can directly write your code out of it. The same in here. And of course, again here, you cannot have low level requirements without code. And, much more important, you cannot have code without high level, without a requirement. So you have to relate it to someone. So that gives us a very good interlink that you do not have any code without a requirement, and you do not have a requirement without any code. So everything what is in your software now is specified. Just a small example, because high-level, low-level system, maybe it's a little bit confusing. Just imagine an automated beer brewing device where everyone wants to have at home. One of the system requirements would be that this device shall signal that the beer is ready, because if you're thirsty, then you're interested in that. So if I'm developing now my high-level requirement, I just state that there is a function called beer ready, and that shall detect if the brewing is finished. And, of course, I just interlink that with my high-level requirement. Because if I cannot explain why I'm getting this idea from, then it is certainly not a good requirement. And then going on the low-level requirement side, I can specify that the brew ready function shall return true, and it shall have the following algorithm. Algorithm, state charts, pictures also can be formulated as requirements. There is a long list, and it would take an hour what a good requirement is. But to summarize it, it must be feasible, it must be realistic, so you can reach it, and it must be testable. And like a bad requirement is, the plane shall hold attitude. Yeah, how you test that? Yeah, you can fly beneath, but it's not a good requirement. To finalize that, also other high-level, or in this case, a system requirement, can be allocated to a high-level requirement. For example, this is a typical safety requirement that you shall not burn the beer, but it has the same high-level requirement, like there shall be a detect function which detects that the brewing is ready. Having that, you get a wonderful traceability matrix, and you can have every requirement. You can do that for every requirement. This is just a few from system level to code, but you can have just a list also for low-level requirement going up to the system level. And in our example, S23 is having two high-level requirements, H14 and H22, having several low-level requirements. And in the code beneath, there you have some markers which just say, okay, where you get the idea that you code that, where is it related to? For small projects, that usually is done by hand. Larger projects, like 4.5 million lines of code, will have some automatics in here. So it's quite good to know, because if you have an inspection of the code, if you just have a look at it, you always know where it comes from. And here we are at the testing. Yeah, as said, if you specify it, you have to verify it also. And the verification heavily depends on the software level. For example, on level E, as said, no testing is required at all. You just code and hope it's working. On level D, you're doing some high-level tests. That means that you test your high-level requirements. There shall be a beer ready function. You write a test case, and if you have written your source code, you can run the test and see if it's there or not. By the way, not always automated tests is the solution to everything. Also, code inspection could be a valuable thing. But as you can imagine, everything you have to do by hand costs even more amount of time. On level C, you also have to do low-level tests. That means everything you have specified in the low-level requirements has to be tested. And you have to have statement, data, and control coverage. Of course, you specify data, and you have to show here that every statement in the code is really required. And every data structure and every control flow has been required. But it gets worse. On level B, it gets independence, and I promise the next slide will be about independence, and decision coverage. That means every decision you do in the code has to be inspected and has to be followed. So that every line of code has to be at least one possibility which is used. For example, if you have an if clause with which never will happen, the else path will never happen, this will be clearly detected by this kind of tests. And even more complicated, there is level E, which is MCDC. It's multiple clause decision coverage, and it will fill at least 1 hour to explain that. To summarize it, it's very, you have very high effort for testing that. You have to have look at every parameter in every clause, in every condition, what the result would be. And something else which is very consuming a lot of effort is the source to object code traceability. As was said now on the high level and low level requirements and the source code, you have here now on object code. So you have to have a look at every assembler line where it belongs to a source code line. You can imagine that's quite a lot of effort. Fortunately, there are certified compilers which are allowed to help you here. Anyhow, a lot of effort. Now, the independence. D178 often states independence. There are two views about that. First is the process view in itself, which says that independent topics will be separated in separated documents, like the design plan and the verification plan and the configuration management plan. They're in separate documents, or at least in separate chapters. And high-level requirements are separated from low-level requirements. Test is separated from specification. But that's not what the D178 intends in here. It intends a personal view. That means dependent artifacts like requirement, code, and test will be done by different persons. And artifacts will be reviewed by different persons than the author. Like if you're writing a source code, then you're not the one who specifies the source code. If you're having a look at a source code or of a test case, then you cannot be the author of that. Review is a very smart method of finding errors in a very formal way, but if you're getting used to that, it's a very helpful process. Also, reviews would take too long to explain in more detail, but if you're interested, I'm happy to explain it in a smaller group. So to summarize that, the D178 is a software development guideline which is accepted by the EASA and by the FAA, and that's the reason why the companies are using it. By the way, they are also using it now because they have just seen that it makes sense. But if you develop something which will not be accepted by the government, then you're not very happy with that. By the way, you can develop with a complete different process, but you have to explain why. Small planes often using different processes because they just said that if they crash, not a lot of people are killed, so that's good enough. Yeah, unfortunately. It contains a description of a complete development process, including specification and evaluation. It does not specify how in detail it should look like, but how the interactions in it and what artifacts shall be here. And it relies, beside other things, on the principle that software shall only contain functionality it has to. This is, for example, also very interesting if you just think on test code. Often you have in your software code which is just used for testing it. But imagine a plane which just starts in the air to run his test routines, putting all rudders in all directions and this kind of stuff. It's not a good idea to have that. And it describes a clean requirement coding test development process with an emphasis of independence that has been proven to find a lot of errors. And it has evolved of experiences on 40 years of critical software development and has facilitated a huge development projects like A380 and the 787, which are really, you can't imagine how big they are as a matter of, in case of software, on a very high reliability standard. That's all? No, of course it's not. But, for example, protected operating systems will be used. Time-triggered operating systems and communication will be used. Mathematical proof of substance will be used. This is a very fancy thing, and companies are paying a lot of money for mathematic professors to do that. Also, they're using proven hardware. No one will get a state-of-the-art computer in a plane. And last but not least, redundancy. Redundancy is often used in software and in hardware. But the most expensive thing in a plane is weight. And if you have 3 computers, they will weigh more than 2 computers. Will work more than 1 computer. And if you can just satisfy the function with 1 computer, you will do that. But still, the DO-178B is the spine of the software development. So if you do something, you will be involved with that. Coming to my conclusion, Peter Ustinov just said that being an optimist is to be foolish enough to believe that the best will come yet. Hopefully it will come. Can we use it outside the aerospace industry? It's a complex software development process. It may get very expensive to do testing. So if you have a look at level E, which just is number of 1, then you can imagine what level A means. By the way, this is just the expected and the real thing. Like, most of the people think that level B will cost much less than level A, but which is not true, and so on and so on. But as we know, or as history has proven, that formal processes may help find errors early, and finding an error early will get it less expensive. That could be a way to just have the trade-off. Investing money and effort in having a complex and formal process versus finding errors very late. I mean, if it's an application where you don't care about an error and the error in a field would not cause a lot of effort to fix it and not a lot of money, then don't invest that in the development process. But if $1.1 billion, maybe they have invested just 1 review, they will be rich. So some methods may be helpful, like the requirement tree. I think that could easily be attached also to non-critical software projects. And the independence and reviews. By the way, new programming methods like extreme programming going that way, but describing it different. Maybe there is some interaction. But a full DO178B is not easy to be applied because it relies, first of it, on a network, and I don't expect any computer to have a DO254 certification for the hardware. And because of the fault tree, meaning what the component can cause on other components, you will probably would have DO178B in all of the components. And imagine Linux fully specified, fully test cased, every assembler line is known where it comes from. I don't think so. But maybe own guidelines could be developed. And the advantage of that is if it's accepted by everyone, then you can use them for multi-site projects. Multi-site in case of multi-components, multi-area, whatever, because they need to trust. If I'm using a component for my critical application, I have to trust all underneath components. So just to conclude, who you can trust, I think accepted guidelines you can trust. But the guidelines are to be developed. I don't see that they currently exist. So that's it. Thank you for your interest. Do you have any questions? Microphone is coming.
What is the most common computing language in aerospace industry?
The funny thing is it's C. Ada has been used quite a while, and it is used. And it is a good language because it gives you a lot of formalism and a lot of checks. But many components are developed in C. Just simple of that. High-level components sometimes developed in C++, but the effort to certify a C++ environment is quite high, so they don't do it.
First, one comment to the previous speaker. I'm not sure if it's true for really safety-critical applications or safety-critical functions that they are primarily programmed in C, because C is not very good for formal verification. And for example, there's Praxis High Integrity Systems in the United Kingdom, which uses Spark, which is an Ada subset with annotations that specify the data flow, information flow, and you can also specify pre- and post conditions and can do a formal verification of the source code. And Praxis is known to achieve industry-wide provably the highest rate of absence of errors. So they have the lowest error rate of any software. For example, they have made the avionics, at least the safety-critical parts of the Hercules C-130J, and also the safety-critical parts of the avionics of the Eurofighter have been done in Spark. But one other thing, I have a slight problem with the wording of the slides of saying requirements, coding, testing, with the testing part, because in aerospace, some safety-critical parts require to be reliable to the point of only one failure in 10 to the 9 hours. That is about 114,000 years. So if you have a fleet with 100 planes, it may not fail once in 1,000 years, the complete fleet. And you cannot achieve that level of confidence with testing, which means testing normally means you look at the system or the module as a black box, you feed input in, and you look at the output and see if the output is correct. And Littlebot and Strygini have shown I think in the late 80s, that you cannot achieve that level of confidence, not anywhere near it, by testing. Yeah. So the DO178B suggests other methods than pure testing, like code reviews and formal verifications, and also suggests mathematical methods, very strongly formal methods. So it's just a question about wording, not to call it testing, but verification might be better.
Yeah, first to the Ada thing, to the development. Yes, you're true, there will be new languages and there are high-level languages in here, and yes, it's very important that you have a language which don't give you the, which does make it easy for you to fail. Because as developer, you're a human being, and you will fail. And that's one of the biggest advantages, that people are inaccurate, because they detect so many things by just failing. But you have to also imagine that it's a long history on development, and new languages will slowly be adapted. And only in military projects, or in projects which, let's say, there is time enough to do that, such new fancy things will be introduced. And of course, there will be in the future some stronger ADA usage or something.
Yeah.
But to the second point, I agree with you. Testing is not only testing lies as maybe you would imagine. It's verification, and it's also the kind why it's called verification causes and procedures. Inspection, reviews, and this kind of stuff is a very important part of it. And also it would not give you 10 by the -9 on proof. You also have to involve hardware in that, and you have to divide that by the number of planes which are on the field. So 10 by -9 seems to be quite a huge number, but if you have 1,000 planes, it gets 10 by -5, because you have 1,000 planes in the air. But yes, inspection and review is the one essence, and testing is not just see if it works. And MCDC is much more than just see if it works, and it's a black box. We really investigate every line of code, every clause, and this kind of stuff. That's why it's getting the effort getting so high.
Yeah, just one other short remark about the automotive industry. Aerospace industry is always seen as requiring the highest levels of software reliability, but that may curiously no longer be true, because automotive industry requires so much software these days. And there was one example. They say that Ford has about 1 million cars per year that have one shared software component that is in all of them. And so having 10 to the -9 reliability may not even be enough.
I can just say from my perspective, I'm also developing reliable software for automotives. First of it, yeah, it's funny. In 1995, BMW just announced one of their cars that it contains more computing power that was needed to land on the moon. And yes, we are currently approaching an area where the computers in a car, there are 50 to 80 computers in a car, and they highly interact. But the aerospace industry is just 40 years ahead, and or let's say 30 years ahead. And slowly, the automotive industry just tended to use the IEC 16508 or something. That's a similar standard, but doing a little different approach, like it's more concentrated on fault trees and fault probabilities to close that, and SIL levels are attached instead of software levels, and it's similar. But it turns out that some of the companies are just having a look at the DO 178B, and I'm really curious how that would go on, because currently there is the initiative to develop a better standard for the automotive industry, but it's not here. And it's still a bunch less of software. Okay.
Excuse me, first a short remark. ADA is not a new language, it's been standardized over 20 years ago. But anyway, my question is about something else. Could you please tell anything about software maintenance? I mean, software changes made after certification. Are there any? And if yes, how are they made and why? And how often?
Yeah. First of it, yeah, I just mentioned the new other spread-offs and this kind of stuff. Maintenance, yeah, that's a very important thing. As you can imagine, you have introduced a lot of effort in just having this piece of software. you may be not interested in do anything else because you finalized, but that's not true. And the D178B just also specifies how you maintain things. And as you have so many requirements, and if you want to change something in here, you have to have a reason. First of it, you may have found a real bug which was not found before, or you have to do something else. And it's also done in a very formal way. By the way, you have to, the whole environment has to be here to reproduce anything on maintenance for 15 years. So the best thing is you freeze your computer somewhere and then you're fine.
So I have a question. This strikes me as a very, I don't want to say old-fashioned, but the software development model is very kind of waterfall. You do requirement, design, blah 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 blah. Is there any direction in the industry to try to adopt some other kinds of well, basically cheaper software development models for aerospace?
Yeah. By the way, the waterfall model is I think it's a good model because you just finalize things before you finalize dependent things. Good enough. The D178 does not require it. It just says you have to have a high level standard, a high level requirements before you finalize your low level requirements. That's all. And if you do it in a spiral way, or if you do it in an adapted V module or a waterfall, it's up to you. To be honest, most of the development I've seen currently just using an adapted waterfall model, because
Okay.
it's the simplest thing to use. It's have the less effort and the people know it.
Yeah, okay. I mean, I guess it makes sense in this kind of highly controlled environment. And my other question is, I don't really see much role for open source in this environment. Does it exist or get used at all, other than email?
It gets used because what is not stated in here, you can reverse engineer every piece of software you have in here. You just have to take care that the full module, every document is in it. And sometimes they're really using that. Like I've seen an IP stack been used. It has been, yeah, it's not a flight critical system, but it has been used. And it has been reverse engineered in as matter to fit to level D. As a matter of fact, you have to specify, you have to find the high level requirement, what it does, and then you have to test cases, maybe by inspection. That's it.
Okay.
So I think, and there's a company which has a Linux kernel which is fully D178B certified. It has at least the API. Everything else is different, but it looks like a Linux.
What kind of operating systems are you using in the aerospace techniques? I think when you mentioned now the Linux kernel, you were talking about the WinRiver?
No, it's Linux system, but anyhow. WinRiver has a lot of companies have some shares in here. And there are a lot of operating systems. The problem is some components require a really full-blown operating systems, and WinRiver and Green Hills have them. They have fully specified operating systems. They cost a tremendously effort of money, and you can use them. But there are also smaller approaches, like just a time-triggered operating system, which gives you the full functionality you need. They are homegrown by the companies.
Do you have any metrics? What's the actual cost or manpower you require per line of code, per level?
No, because that heavily depends. I was aware that this question will come, but it's really quite simple. If you have a development environment which is used to have formal processes, it costs you almost nothing more than just writing the documents. If you have a development environment which is not used for it, it can put you millions of euros and millions of hours. So it really, you have to have a look at your development environment, how you're used to it, and see if that matches anyhow. Okay, I think we really have to hurry on now.
I have just one remark to the open source question. I read last week at Heise news ticker that Airbus started an open source project, and they want to promote the open source software to use in the aerospace industry. Perhaps you can search at Heise last week.
Mm-hmm. No, I was not aware. Curious, yeah, it's interesting thing. I mean, open source is the perfect ground which can be used for that, because everything is open. You cannot certify Windows, not because it's not open, but because of several reasons. But
the point is, if you use open source, you have to be always on a level where you don't just change anything, because you have to make a certification of this special version or the special versions of the particular source code files. I think that is a big problem in open source then, because you have to be the software development process have to be well defined.
But I agree with you. But on the other hand, open source does not directly relate to it changes every time. I mean, there are a lot of modules in the Linux kernel which have not been changed till 2.6 is maybe different, but 2.4 which has not been changed for years. So if it's good, if it does what it is suspected to do, why change it? So maybe if you have additional questions, I will be in here, but so we have to leave the room. Thank you very much.